But you have to manage your lifespan, because while it's very easy to take that kit and write some software that does networking, it's rather useless if you have to replace the batteries every 2 days. Okay? With all of your laptops, you know that they're not really wireless, and that 3 hours later you've got to go chasing a wall outlet. So with these, you don't want to replace them for months or years if you can get away with it. And that's done by keeping the CPU off as often as possible. And I'll be going over its power modes later, but you can even turn off the main system clock or even the crystal that it synchronizes its time to. You can do intelligent routing. So on a PC or a server or in a networking environment, you're trying to run as much traffic through the network as possible with as little latency as possible. Here, I'm only trying to get a sensor reading once per minute. What do I care if it's 3 seconds late or if it has to go through a couple more hops? I don't at all. But if the battery of a router dies and that cuts off a leg of the network, I've suddenly lost a lot of the value of the network. So the network has to use mesh routing so that when a unit dies, whether it's stepped on or hit or its battery runs out, it has to be reparable. The network has to heal around that area, and if possible, it should do it beforehand. If a given router is running low on power, it should be able to switch to not being a router before its battery dies. And exactly when and how to do that is an open area of research. No one knows the best algorithm for doing this. You also need to reduce your listening time, because listening is almost as expensive as transmitting. And a transmission is very short. So in the case of a normal transmission, you do a clear channel assessment. So the radio will listen to the channel for a bit to make sure that no one is transmitting. And so long as that channel is in use, it refuses to transmit. So if you also have Wi-Fi on the same channel, it will delay its transmission until the Wi-Fi transmission is ended. The problem with this is that the clear channel assessment, even if the channel is clear, consumes more power than the broadcast. So if you broadcast twice, instead of doing the clear channel assessment, and you just assume that one of the two copies will get through, you actually save battery power if your guess is often correct. So the setup is very different from PC networking. You need to make your protocols assume that half of the packets will be lost, or at least survive it. You need to not listen for confirmations of reception, because that wastes battery power and that wastes time. And if you do this properly, you really can make a little circuit board with 2 AA's last for years at a time. Now, you also need to make these things cheap. The idea is a slogan called "stick it and forget it." The idea is that the sensors should cost less than $1 a piece, and that the time of an employee to replace the batteries of that sensor will be more than the time, or than the cost of simply replacing the device. So inside of your factory, you just have a huge box of these things, and when you're ready, you just pop the battery in, stick some gum on the back, slap it onto a chemical tank, and then you know the temperature at that point. The reality of this is that it will cost you $10 to $20 per radio for manufacturing costs and similar things, and that's if you're optimizing it. We're looking at about $30 wholesale for our belt buckles. So they're not quite to the point where you can just slap them up and forget about them, but they will be within 10 years, which is why it's important to learn this technology now. Because in 10 years, these systems will be controlling industry. They'll be controlling chemical manufacturing. Scada vulnerabilities are a hot topic right now, but there it's just that the command and control systems are incompetently designed. They don't use cryptography, and they think that they can get away with it because there are no radios in the line. With these, you have an open radio, and cryptography isn't the best. The radio chip actually does the cryptography and not the CPU. So if you take one of these boards, you can stick 2 needles into it and capture the keys as they're sent from the CPU to the radio. And because you have to have a key loaded in advance of receiving a packet, you have to share a single symmetric key across your entire network or else you lose packets that you don't have the proper key configured for yet. So you have to either do very complicated scheduling of keys, or you just say forget it and use one symmetric key that can be stolen from any device simply by sticking 2 needles in and hitting the reset button.
So here's an example of a simple mesh network. We start here with the source, and it's trying to communicate with the sink. So like an IP network, it will try to find the shortest route to the sink. But that's not all. That's the most important thing about these networks is optimizing battery life for all nodes in the network so the entire network can communicate with the sink.
And any node can become a router when it likes under many of the designs of these networks. So instead of having nodes that a priori are just routers or just sensors, in many of these designs, all of them are sensors, and whether or not it's a router is decided on the fly. Yeah, continue.
So,
yeah.
Next slide.
Oh, sorry. So the idea is that these will automatically set up a mesh. They'll automatically decide that the 2 sensors at the top will forward toward the sink. And then the other 2 radios automatically decide which ones they're going to route through. Now, when circumstances change, for example, the ones that are only transmitting, you can use very little power because they don't have to receive anything. And they don't have to wait for any packets. They don't have to waste that electricity. They can wake up, do a burst transmission, and be done. So the routers will fail first as far as battery consumption goes. But if the units are close together, there's no reason why that's the only router in the region. So the network can automatically reconfigure itself to route differently, to save electricity, to save battery life, and to extend the lifetime of the network. And the packet sizes are also worth considering. They're a hell of a lot smaller here than in anything else you'll deal with. Every 15.4 packet has a hard limit of 128 bytes, which is 1/512th the size of a UDP packet at 64 kilobytes. And it's also 500 times smaller than, and that same UDP packet is equal to the size of everything inside of the CPU. All flash memory, all RAM, all I/O, everything. You cannot store a full UDP packet within your average wireless sensor.
Belt buckle.
Belt buckle, right? Belt buckle, Tennessee. We're being neighborly here, okay? So you have to design applications for these things, realizing that they are not computers, that you don't have the bandwidth, that you don't have the protocols. Even though a variant of IPv6 is available, you should never treat it as if treat these devices as if they were PCs. Never stream video over it, never stream audio. For the love of God, don't run BitTorrents over these things. I mean, you have to design it for the application at hand. And a lot of these protocols are being designed by committees that aren't necessarily considering that. So if you, say, demand packet fragmentation to allow for very large packets, not only have you shot battery life, but you've also dramatically increased the cost of the CPU for each node. So this is the sample platform that we wrote the party mode software for our application on. And these are targeted by TinyOS. There's a JTAG adapter on the top, but usually they're programmed through a serial bootloader. So you plug it into your USB port, you type make tlosb install in your project directory, and then all of the software is installed to it, and it runs your application. There are Ubuntu packages for everything here. You don't have to build your own compilers or do anything terribly complicated to begin to develop for them. It's got a 16-bit microcontroller with 48K of flash ROM and 10 kilobytes of RAM. It has analog to digital and digital to analog converters, but there's also a inside of the MSP430, but there's also a separate chip for doing the same. It has hardware serial ports for communicating with the PC and with the radio. That becomes important when you try to reverse engineer these devices, because serial buses will always run to the hardware serial port on the chip. So by looking at the data sheet, you can determine that the radio, for example, will be connected to one of 2 pins, or one of 2 sets of pins. There's a ChipCon 2420 radio. This was the first Zigbee radio that made it to market and was practical to use. So all of the